Okay, so welcome everyone. So it's a great pleasure for me to introduce Sophia Lien. Sophia is a visiting student, so she's coming all the way from Taiwan. In fact, she's currently a doctoral student at Yanming Jiaotong National University in Taiwan. And then her research expertise is reinforcement learning, but also uncertainty quantification to develop robust techniques. And so this is what she'll tell us about today. And so without any further ado, let's welcome Sophia.
Thank you for the introduction and thank you for having me here. I'm happy to share our work related to robust reinforced learning. So in today's talk, I'm going to share why we need the robust reinforced learning and what kind of scenario we need to consider about this, and also what kind of method we have. So in the beginning, I'll have a brief introduction of the reinforced learning and talk about this reality gap in a different scenario. And at the end of this talk, I'll have talk a little bit about what's my current and future research direction. And in today's talk, I'll share 3 of my papers. And the first 2 of them are published at the ICML, and the third one is published at EGCAI. So let's first talk about the high-level idea of the reinforced learning. So we know that there's lots of applications here, right? Like play game or autonomous driving, play Go, or even nowadays we use the reinforced learning to fine-tune our model. And more than that, because during the COVID-19 pandemic, the Greek government also used the reinforced learning model to help them to do the border control. And also the institute in Swiss and DeepMind, they try to use the reinforced learning model to have the control on nuclear fusion. So lots of application nowadays. And what is reinforced learning doing is all about the agent environment interaction. So there are several components here: state, policy, action, and reward. And this cycle continues repeat. So in reinforced learning, we use the framework of Markov decision process. So in this Markov decision process, we have state space, action space, transition operator, and also reward function. So how we transit our state, it all depends on our transition probability. And we use the value function to estimate what's the total return we will get during this decision-making process. And based on the framework of Markov decision process, we can estimate the probability of our trajectory. So the goal of reinforced learning is to find an agent that could have to maximize the total return we will collect it. And from this objective function, you can see why reinforced learning is different from other supervised learning. Because the first thing is, take the image classification, for example. Every time the model makes the prediction, it has no correlation with the future prediction, right? But for reinforced learning model, even a small differences in the beginning, it could have very different result in the end. So in reinforced learning, we care about the accumulated consequences. And another thing is that in supervised learning, we always have the label. We know what's the right thing to do. But in reinforced learning, we need to explore it by our agent itself. So we have no answer what's the best. And the agent need to find out by itself. And there are many ways to find the optimal policy, right? So we have value-based, we have policy-based, and we have the adaptative base. But that's not what the main part I want to talk about. Today's topic is more about what is our training data source. So we just talked about the reinforced learning. It's all about agent environment interaction, right? So what is the environment here? We have several choices of the environment. So the first choice is real world. So it means that we can train our model in the real world, but we know that it's very expensive and dangerous. So another solution is we can use simulator. But not all it's safe and it's efficient, but not all the case we could have a reliable simulator, right? Like in health problem situation, it's hard to have a reliable simulator to predict our health. And also like a financial market, it's hard to have a reliable simulator in for the financial market. So in that case, we have historical data. So the problem is that can we use historical data to train reinforcement learning model? And that case is offline data set. But no matter what kind of data source we use, maybe from the simulator or from the offline data set, it's hard to have a transition probability that could the same as the transition probability in the real world, right? So since as long as there is a small difference in the beginning, it could have very different outcome. So can we reduce the negative impact when we deploy our model in the real world? So that's the main issue we want to talk about today. So the first part I want to talk about is the challenge in simulator. And here I'll share the method in our paper, Revisiting Domain Randomization via Relaxed State Adversarial Policy Optimization. So now we are focused on the gap between the simulator transition probability and real-world transition probability. This kind of problem we'll call it sim to real. So a common technique would be the domain randomization. The core idea behind the domain randomization is now we have the simulator. Maybe we can just perturb the environment parameter of the simulator. Then we have different kind of condition of transition probability. If our agent could survive from this different kind of generation probability, and it means that our model is robust enough. So take the couple, for example. In this case, there is a pole standing on the car, and the goal is to balance the pole by moving the car left or right. So if we want to apply domain randomization in this kind of task, so maybe we can change different length of the pole or different weight of the pole or different friction coefficient between the car and the ground. But and this method is easy to implement and very straightforward. But there's still something is unclear, like what kind of environmental parameter I need to adjust. So I just adjust the length of pole and the weight and also the coefficient, the friction coefficient. Are they good enough? Or do I need to consider more, like the speed of wind or even the gravity, right? And another thing is, and then what's the range I need to adjust? So if the task is too difficult, then our agent may just fail to learn. But if it is too easy, then our agent might not good enough. So in our paper, we rather than use the domain randomization, we use the state randomization. So it means that we add the perturbation into the state space directly. And this allows us to bypass the question, what kind of environmental parameter we need to perturb? So in domain randomization, the uncertainty set is different environment parameter. And in state domain randomization, the uncertainty set will be different size of perturbation. But there is there is still one question we need to answer, right? So what is the size of perturbation we need to use? And so again, too difficult, fail to learn, and too easy, not robust enough. And in order to see how important this question is, we use a simple real-world example to see. So this is the algorithm for the state adversarial perturbation. And you can see, because we consider the state adversary perturbation, so when we update the value function, we will consider the worst case value in the neighborhood. And our policy is a greedy policy. So the setting of this grid wall is there are two terminal states. And one is this goal state with yellow star. And another one is a trap with the red cross. So at each time step, our agent will collect -1 reward. And if it reach the trap, it will collect -10 reward. So the goal is to reach the goal state as soon as possible. And the color map here represents different value of value function in different update iterations. So blue color here means high value, and red color represents low value. And the direction of an arrow means the decision making of our agent. And by the 12th iteration, you can see if the agent is just next to the goal state, it knows it needs to reach the goal as soon as possible. But otherwise, the agent just like a random policy. And what is the worst is if the agent just next to the trap, it would jump into the trap directly. Why this happen? Because for that agent, I think the perturbation would happen all the time. So instead to collect -1 reward for each time step, it just choose to jump into a trap directly. So it means that if your task is too difficult, your agent will be too desperate and do something that you don't want. So it's very important to have, once you have an uncertainty set, it's important to have an adaptive learning scheme to train your agent. So before we introduce our adaptive learning scheme, we'll first introduce a relaxed state adversarial method. And the core behind this method is relaxation parameter alpha. So we use this alpha to define a transition kernel called relaxed state adversarial transition kernel. Basically, this kernel balance the transition probability between the nominal case and worst case. And in the paper, we prove that this relaxed state adversarial transition kernel is actually can represent the average case performance under the uncertainty set. And based on this finding, it allows to formulate the relationship between average case and worst case. So this page is want to describe what's the relationship between the worst case performance and average case performance. So left side of inequality is the worst case performance. And there are several terms in the right-hand side. And the first term is average case performance. And other terms are other factors affect the difference of the performance. And you can see, so the right side is the lower bound of worst case performance, right? And you can see different alpha actually have different worst case performance lower bound. It means that we can find an optimal alpha to improve our worst case performance most. So by this knowledge, now we are good to design our adaptive learning scheme. So in our paper, we use a bi-level approach. At the upper level task, our goal is to find the optimal realization parameter alpha that maximizes the lower bound of worst case. And at lower level task, we have a fixed realization parameter because this realization parameter is designed by the upper level task, and it's designed according to the current ability of our agent. And under this fixed realization parameter, we will optimize the average case return at the lower level task. And in this paper, we use the Mujoko for our experiments. And so the first thing is want to see what's the average performance and worst case performance. Why it is important? Because for those methods, some of methods, they only focus on the nominal case. It means that as long as they face the worst case scenario, then they will fail. And some of methods, they focus on the worst case scenario. It means that, okay, they can do good thing when the worst case happen. However, they forgot to take care of the average case performance. So even though there is nothing bad happen, their performance won't be good. And in our paper, we focus on both to improve both of the performance. So the horizontal axis is the training step, and the vertical axis is the performance. The orange line represents average case performance, and the blue line represents the worst case performance. And you can see from our adaptive learning, because we choose the alpha adaptively, depends on the current agent's capability. So we can improve the worst case and also the edge case performance simultaneously. Another thing we want to see is that, remember what's our goal? We want to reduce the reality gap, means that we hope our agent can survive in different kind of transition probability situation. So here we want to see if our agent can survive in different environment parameter settings. So the horizontal axis means different size of robot. So it means the density of the robot will be different because the size will be different. And the horizontal axis means different gravity. So in different kind of gravity situation, can it still move smoothly like this? The red color means our method outperform domain randomization. And you can see in most of the condition, our method can have a better performance than the domain randomization. So one takeaway of this section is that when we consider the uncertainty set, it's important to have an adaptive learning scheme, and so that you won't have a too conservative or too desperate agent after your training. So anyone have?
Yeah. So during training, if I understood this correctly, during training, you're only perturbing the state, is that correct?
Yeah.
Only the state is changed?
Yeah. So during stay, we only perturb the state, but we didn't move the we didn't change the transition probability. So we only have the nominal setting of the simulator, but we didn't change any environmental parameter in our training.
Okay, so how then is the state changed? Is that like is there a noise that is associated with the new state? Like let's say in Juku, let's say there is a robot, let's say there's an ant that is making move. Now, does that deterministically move to the next state, or is there like some Gaussian noise added to the state?
So during training, because we only have the nominal transition probability, so we don't exactly move our agent to the worst case scenario, but we just use the calculation to calculate what if that situation happened, then what the value is. Then use that to update our model so that our model knows what's the value function that would be. So all our state, action, and next state are all from the nominal transition probability. And the way we find the worst case next state is still using the value function to find that. So we don't have to perturb our agent in the simulator.
So you have a model. It's like planning. So you have a model that you use to find the worst case state.
For the worst case, we use the value function to find what is the worst case. So we will define the largest perturbation, and we know how to find the worst case in this neighborhood.
Okay. And then can you go back to the previous slide where you had like this heat map?
Yeah.
Not this one.
Okay.
Can you go forward? This one. So now the different environmental parameter settings, is that again different states or what is different?
Yeah. So here, because it's already in testing, so now we perturb the simulator directly. So during training, we only have the nominal setting for the simulator, which means that we don't change anything and we don't perturb that in the simulator. We only calculate for that. But during testing, because we want to see if our model can survive in different kind of transition probability situation, so we change the setting of the environment parameter in the simulator in testing phase.
What is the environment parameter?
The parameter are the size of robots and also the gravity. So the size of the robot means that the density will be changed, because once you change your density, maybe because the task is to control every joint of the robot. And as long as you change your density, if you still use the same way to control your robot, then it may fail, or it may fail easily. But it means that even though we change the size of robot, our models still can survive from this kind of situation.
And with respect to performances, do you compare the performance to other offline methods that don't do any state perturbations or other simple? So do you compare to other like traditional offline methods?
Sure. So for the so we still in our case we still can have good performance in the nominal case, because other method like only train in the nominal case, and we still can have good performance in nominal case. And if you see the paper in the domain randomization, maybe they have the general capability for different setting, but their performance at the nominal situation may not so good, just maybe would be a bit lower. But in our case, we find that we still can have very good performance at the nominal situation. And I think maybe that's because our training is adaptive learning, means that we will change the distribution over the uncertainty set according to our agent's ability. So if our agent forgot what happened in the nominal case, the alpha will change, will adjust.
understand. I thought in domain randomization, it's not like you change the initial setting of the environment and then you went with that thing. But in the algorithm, it was like on every state we are changing it. Is it, which one is the case? Like, is it once changing the parameter setting, or is it on every state we are?
So for this setting that, for example, the 0.6 for the size and 1.4 for the gravity. And for this experiments, we only do under this setting.
Also, it's fixed.
Yeah, so it's fixed.
For the formulation that we had for the, there was like some slides before this. No, the one with the probability of the state with epsilon and before. Yeah, this one. So what would happen in the discrete environments? Because I understand that like for continuous cases, we can have this noise, but what about the discrete environments? Because it seems that it will give you a worst case, a state that doesn't exist.
Oh, yeah. So in the grid wall example, the worst case, we still use the one grid. So so it still have the same length of the real grid. But because so this perturbation will be kind of we imagine that we can have 1 minus alpha's perturbation like this. So that what the alpha here doing is that actually it presents it's kind of distribution concept. It means that there is an alpha probability that nominal case would happen, and there is 1 minus alpha probability that worst case would happen. So that's why our agent can do both on each environment. I'll continue, but if you come up some question, we still can come back. Okay. So another challenge is in offline data set. And here I'll introduce the method that we use in the enhancing value function estimation. So first of all, the state action dynamics in offline reinforcement learning. So now what we are focused on is the transition probability induced by the offline data set and the real world transition probability. But before that, before we talk about what's the challenge, please allow me to highlight the importance of value function. Because when we update our value function, we usually use the Bellman equation to update, right? So it means that the value is the immediate reward plus all other reward that we will collect in the future. And how we update our policy is that try to find an action that will maximize our value function, right? So the important role of our value function is to guide our policy. And let's see what happened in offline data set. So take this simple maze 2D, for example, the goal is to reach this goal area. And the road is in white and the wall is in gray. And each black dot here means the data set point. And so it has the information about the state, action, next state, and also its reward. But when we update our value function, we still use the Bellman equation, right? But as long as our model try to do something else, because now we only have the information about the action already taken in the data set. And if our model want to try something new, we don't have that information. So the only thing we can do is use the value estimation of that data. And this kind of data, we call it out of distribution data. And also, when we update our policy, our policy try to find an action that maximize the value function. But if the policy try to find something new, explore something new, then it's still an out of distribution data. So it means that in offline reinforced learning, the policy update rely on the value estimation of the out of distribution data point. And let's see what happened. So this color map indicates the value of the value function. And the yellow color here means it has a high value. And the dark blue color here means it has a low value. So it looks quite good, right? Because our model knows here is important state, it's a goal state. And because of this corner is far from the goal state, so it has the lowest value. But what about our policy? So this is the decision making made by our policy. If the start point is at the top left, then our policy know how to reach the goal. And if our agent is start from the top right corner, it also knows how to reach the goal. But what happened here? If our policy start from the bottom right corner, it will choose bump into the wall directly. Why? We can see that, let's back to the value function. We can see the color change rapidly here in the wall area. And it means that there is a steep slope in the value function here. But actually, we don't have any data point here because it's the wall area. So it's all made by our model estimation. So if we can encode some environment dynamic information here, it can help our model, help our value function to guide our policy better. So that's our goal, how to encode the environment dynamics information into our model. So before we talk about our method, I want to highlight that most of our reinforced learning are discrete time reinforced learning because it's more practical. So discrete time reinforced learning here, it means that for the decision-making process, we can discretize it into discrete time steps. And there is another method, it's called continuous time reinforced learning. So in continuous time reinforced learning, they will formulate the dynamic system in the partial differentiable equation. And in this case, our value function will be the integral over the reward that we collected over time. And using the dynamic programming principle and also the first order Taylor expansion, we will have the Hamilton-Jacobian-Bellman equation. Here means that from the continuous time viewpoint, we can separate our value function into several components. The first thing is the immediate reward. And the second term is related to the state dynamic. And the third term is related to action dynamic. So it means that if the first derivative of our value function with respect to S can match the direction of the state dynamic, then we have a higher value function. And if the first order derivative of our value function with respect to action match the direction of the action dynamic, then we can have a higher value function. So you can see from the continuous time viewpoint, they formulate the value function here from the environment dynamic viewpoint, right? So here we want to borrow this idea into our discrete time reinforced learning. So the first part is the standard discrete time reinforced learning. And now we have the regularization of our value function. We hope that from the first order derivative, it can match our system dynamic in the data set. So this is how we encode the environment dynamic into our value function. So after we encode this system dynamic information, you can see that our value function have better information or have better knowledge about the environment. Hence, it can guide the policy in a more reasonable way.
How do you get as start?
So, because a start here means that the change between the state. So in the data set, we have the state, action, next state. So we can use the finite difference to calculate the state and next state to get our S star here.
Just the S prime minus S.
Yeah.
So then this brings another question. So here you mentioned you want to model the dynamic. Why don't you use some generative model to model the dynamic?
Yeah. So it's quite tricky that if I use the model, I have a generative model to model the environment. It would be more like a model-based method. But in our case, we want to have a model-free method, but we encode the environment information here. So you can say that our method is between the model-free and the model-based.
Okay.
So yeah, so you can do that. You can have a model, and so to formulate to estimate what's the transition probability first, and use that to train your model. And usually in that case, it's easier to train. But because you're in a model base, your model, so you would introduce another gap here because your model would never just the same as the data set. And the data set is not never the same as the real world. So I think it's a trade-off. You can do that. And actually, if you do that, it's easier to train your reinforcement learning agent. But
is any compare in your paper to compare to another ways?
I do have some. Yeah. I think that's in my appendix. We do compare to the model-based case, but I think our performance is outperform Low's method. Yeah. So usually in reinforcement learning, we will separate them. So for the model-based algorithm and or model-based algorithm, this kind of thing. So it depends how to distinguish this algorithm. It depends on, do you learn a transition probability directly? Any other question regarding to the algorithm? Yeah. Okay. So in this paper, we are other than the mutual code, we have more environment, utilize more environment in D4IL. So we have Franca Kitchen and a joint hand, or also the MMAs. So like the Franca Kitchen, the goal is to open the cabin, move the kettle, this kind of stuff. And the more efficient you move your agent, then the higher reward you will collect it, this kind of stuff. So you can see because our model encodes the knowledge of the environment dynamic. So we can have a higher performance in the offline data set. Yeah. So the takeaway here is that in offline data set, because we always use the out of distribution data to update. And it's hard to control what's the model estimation of that out of distribution data point, right? So if you can encode some environment dynamic into your model, then your model can have more reasonable action here. Okay. So the last topic is challenges in offline non-stationary environment. And here we'll introduce the method in contrastive learning and reward smoothing for deep portfolio management. So now we are focused on the offline data set. And what's more different is that the real world environment of this kind of data, that's non-stationary environment. It means that the transition probability will evolve along the time. So in order to explore what's the key component in this kind of problem, we use the finance problem called portfolio management to explore. So the portfolio management is to organize your investment, which kind of asset you want to invest or how much money you are put in like this. So the goal is not only to maximize your return, but also to balance the risk. And in this kind of problem, the state, we use both external state and also internal state. So external state, it means the historical data prices. And internal state means the weight of asset in our portfolio. So the action would be how to, at each time step, how to reallocate your weight for your portfolio. And then what's your portfolio value? So your portfolio value will be the initial money you put in times what's the ratio you put in each asset, and also what's the price change for each asset, right? And for the calculation simplicity, we use the logarithm of portfolio value as our reward function. Okay. Now, after this setting, you are good to train your portfolio management model. But after you training, you find that maybe you can have a good result during the training set, but for the testing set, it always have the bad performance. Why this happen? Because each time period, we could have different financial market sentiments. So our question here is that possible to have a single model and can effectively handle this non-stationary transition probability? So one famous technique to deal with this to want to have a robust model is contrastive learning, right? So the core idea behind the contrastive learning is to gather similar data together, right? So what is similar data here? In computer vision, we can augment the image. So we will have the same image, but in different color. And we know they are same image, so their representation should be gathered together. But how about in the financial data? How to define which data set or which asset are similar asset? So in order to capture the nonlinear relationship between assets, we utilize a graph neural network called neural relational inference. Here, the way we define which assets are similar by if they can predict each other's future price movement, then we say they are similar. So here, our goal is that we not only want to use the historical price movement, we hope that this kind of representation could have the prediction ability and use the prediction ability to define whether they should be gathered together or not. So by this defining, and we can use the neural relational inference model to decide which data have the highest score. And if they are similar, then we will gather them together using the contrastive learning skill. So in this task, what we are care about is what is the core feature and what is the core feature that could have the prediction ability. And here we use the US stock market for our experiments. And we also consider different kind of finance sentiments. So when the price is going up, or when the price movement did not move a lot, or when the price movement is going down. And you can see that our method can hold, compared to the traditional method, our method can handle different kind of condition. And especially like 1.69 here, it means that we can have a 69% profit in 2 months. So, okay. So does anyone have a question on this section? Yeah.
So does it mean that you can beat the market?
Yeah, everyone likes that. I hope so. I think we still try to so we still try to implement some platform that can encode more information here. And here we only use the price data as the input.
Because the conventional wisdom is that's buy and hold, right?
Yeah.
Or 60 years.
Yeah.
That's it.
Exactly.
Yeah.
So those results, do you take into account transaction costs, like for instance, I guess commission and also the spread that you would implicitly end up paying each time you do a transaction?
Because here we compare to the previous paper, and they didn't consider for the price spread, but they consider the commission. So we use the same commission rate as Lien. Yeah, but in the real world, the price spread will be very important factor here. Yeah, and also we have the experiment in cryptocurrency. And for the cryptocurrency, because you can trade in 24 hours, and then we can see a higher profit in the cryptocurrency. Yeah, but yeah, I don't know if there's a data set, and I think for the because I haven't dealt with that data set with the price spread, I think that would be more interesting and more practical. But I don't know if there is an open data set to consider the price spread.
Oh, I see. So the price spread, yeah, you just need to have data that has the bid and the ask.
Yeah.
And it is available out there, but maybe it depends, like, I think that data account that would like to trading, your broker might be like that available. But otherwise, like just trading on the web, I'm not sure that it is. But since,
Yeah. I think maybe that easier to get the data from the cryptocurrency, because I think cryptocurrency data point are more accessible because before there's also a research line that is related to combine some news information, but after one point, because they use the Reuters news, and the Reuters asked them to not share this news publicly. So that's why we cannot use that kind of data set. Yeah. So to summarize that, today we talk about different kind of challenges from the simulator, offline data set, and non-stationary. So in simulator, we talk about why it is important to have an adaptive learning scheme. And in offline data set, we talk about why it is important to have the environment dynamic information. And in non-stationary environment, we apply the technique called the contrastive learning, but it's not clear how to define what is similar data in finance market. So here we use the prediction ability to define the similarity in finance data set. Yeah. So that's my research related to robust reinforced learning. And now I'm more interested about can we have an agent that can deal with totally new task without fine-tune or without any training, this kind of problem. Yeah. Besides the reinforced learning, I have some other work that related to the uncertainty qualification or like generative model, this kind of stuff. And as I'll be here for 6 months, so I'm very happy to have further discussion if you are interested. Yeah. So thank you.
Before we do questions, maybe just to add to what Sophia was saying, so that, yeah, she's gonna be here for the next 6 months, but if some of you want to talk with her, let's say this afternoon, then she will be meeting on 2310 from 3:30 to 5 p.m. So by all means, feel free to just come and ask her about any of the works that she mentioned here or anything else that you would find interesting. But I guess, yeah, let's go ahead now with some questions, and if some people also need to go, feel free to. Yeah.
Yeah, thanks for the great talk. I really like the idea of reducing learning. Yes. I just have a quick question about the trade-off between the robustness and the overall effectiveness. Because typically in adversarial training, there will be a trade-off between the robustness and accuracy. So I was wondering, did you observe the trade-off in your experiments with the state adversarial policies, or can you obtain a better trade-off with your method?
Yeah, I think that's a very important question, especially we found that in the domain randomization, they usually, because they just directly train in the range of the different setting of the environment parameter. And so they could have an average performance there, but usually they don't have a very outstanding performance for the environment. But I guess, but that I think that problem is not so serious in our method, because we can see even though in the nominal environment, our performance is comparable or even outperform for other method only trained on the nominal case. And I think that's because the benefit from the adaptive learning. So because in our training scheme, we will adaptive change the distribution over the uncertainty set so that it won't forget certain skill it done before, like that.
Like the methods can have an overall better performance compared to other baselines.
Yeah. So from our from this experience, we found that we don't observe a serious trade-off result here.
And like because typically you can like up to maybe it's still good on the original environment or unperturbed environment, but slightly worse than others, like because other methods can be overfitting on the condition environment, but yours can be more robust.
Yeah, actually, I can find that if my model have really outperformed in the nominal case, then that agent would not so good in the worst case. But if I can have just comparable performance with other baseline method, then usually we will have a better performance at the worst case. So I mean, this is the performance for the other baseline. If I train an agent, it could have a very high performance in the nominal case. Usually it would have a bad performance in the worst case. So that's what I can see. But now, as long as we just want to have a comparable performance, then the worst case performance would higher than ours.
Okay, let me ask a question. So, if for your last part, it seemed like it was also done with offline data.
Yeah.
So then, is there a value in maybe combining the approach of the first part with the last part?
Yeah, I think it's possible, but the difficulty would be here we care about the environment dynamic here for this case. And in this case, the environment is a stationary environment. So the dynamic information will be consist in this data set. But if we want to apply that in financial data, I think the difficulty will be the dynamic information in the data set would not consist. So if we can find some core information that consists in that part, then I think we can combine them together. So it's hard to combine them together directly, but as long as we can extract some constant factor layer, then it can combine, or we can use that.
It's pointing out that the financial data is not stationary. And if it was stationary, then maybe the first approach would work.
Yeah.
But I guess one could argue that the financial data is not stationary in large part because the environment itself is adversarial. I mean, the other players in the market are also trying to compete.
Yeah.
And maybe a lot of the non-stationarity actually comes from this multi-agent aspect where there's competition and it's adversarial, right?
Yeah.
So that's why it feels like, modeling robustness by introducing an adversarial aspect seems like a good fit here.
Yeah. I've tried that also. And actually, then the challenge will be, as long as we want to have the value function in the finance market, it's become hard to train. So in this method, we use the policy gradient model for our policy. It means that we don't have the value function. And in the method, we use the state adversarial method. We need the value function to have the idea of what's the worst case state. But I think maybe it's because the value is too hard to predict in the finance market. So as long as we have the value function in the finance data, then the performance is hard to beat the policy gradient method.
Yeah.
Yeah.
Sharing is done on historical pricing.
Mm-hmm.
But when it testing, are there not like any scenarios that use real world prices like real time?
Yeah. Yeah. So in our case, we can only use the back test in our experiments. And so for using the back test, we also need to have some assumption. Means that, for example, you are not a major trader here. It means that for each of your trading, it won't affect the market. So it won't affect the price movement in the future like this. So.
No, but I think what he's pointing out is that you could also do what is known as paper trading, right? Where you simulate trading for real, but it's in a fake account that doesn't actually do any transactions, but I guess the broker will kind of just tell you if your transaction would have succeeded or not. because normally it's the one placing the action for you,
Mhm.
right? So like you could test things, going forward, so not back testing, but with paper trading. It's just that then the evaluation would take a long time because I'm not sure how many transactions per day were involved in those results. If it's just one transaction per day, then you have to wait for a long time.
But what's the difference between the back test?
So a back test, you essentially evaluate by playing back what has been recorded
Yeah.
in the data,
Yeah.
right? And there's a risk of overfitting
Yeah.
here, so it's always questionable to what extent this is accurate. Whereas when you do a forward test, meaning it's now with the market, but without recording the transactions for real, then there's no problem of overfitting. But you're right that it still has the issue that now you don't know what impact on the market you could have.
Yeah.
That's the only thing missing. Otherwise, yeah, it's free from
Yeah.
overfitting issues.
Yeah, I think for our case, like especially in the US stock market, it's hard to have the forward testing because we use the daily data. So yeah, but during our submission, the reviewer asked us to have the test for the more close, more newest period. It means that maybe what? Maybe this year's data or this kind of stuff. So we do this kind.
The second paper that you talked about,
Mhm.
how does that algorithm work in terms of sample efficiency? Because it's like something between model-based and model-free.
I think the idea is between the model based and model free is that because in model free we don't have the model to model the environment, but because now we encode some knowledge of the environment, so I would say it's more like a model free between model free and model based method.
But like, how good is it in terms of like how long it takes to train something like that?
I don't think it increased the. I don't think it increased the training period too long. Because you mean that would this training process become too long because I added?
If I compare it with the regular offline learning, is it better?
Oh, okay. You mean the performance wise, right? So these are quite classic other offline baselines. Like I think the Rebag is quite new, is 2023. And all other are very classic, like IQL, CQL, or TD3 plus BC. These are classical baselines. And these are all model-free method. And we also a model-free method, but we try to encode some other information. Yeah. So overall, we have a better performance.
But with the same, like everything was the same for you?
Yeah.
One last question.
Yeah, I just feel like have you thought about collaborating with like industry, for example, using a method of self-driving testing, for example, because self-driving testing are usually done in the real world. Because your method can help bridge the gap. So I thought maybe it's a good idea to do it with industry.
Yeah. I haven't tried the first two with the industry, but the third one we could collaborate with the bank.
So you try with the real time training?
I don't know how they try that in the real time time setting, but we try that in different kind of market because I'm from Taiwan, so they try this method in the Taiwan's data.